Hi everyone, in the LLM optimization lecture 5, we will cover the most important serving technique, which is batching, continuous batching, and in-flight batching. First, we will cover what is an inference serving system, and then two problems that they face, and the solutions that this paper Orca proposes. So what is an inference serving system? To use generative models like GPT in real world, we often delegate the inference procedure to separate services. So instead of one engine, we have a front end, which is the serving system, and a back end, the execution engine. Because we want high throughput and low latency. Therefore, one example is a vLLM is a serving system that does the front end work, creating an endpoint such as HTTP slash like a chat completion v1. So the user will query this endpoint. The front end will forward this to the backend execution engine, which consists of PyTorch or TensorFlow or faster transformer. Then the results will be returned to the front end and then back to the user. What does the front end do? Not only does it expose this endpoint, but also does scheduling. What if multiple users submit their requests at the same time? Which one should you pick first, and how to group different requests into one batch to facilitate execution? Also the memory, which is a KV cache. This is very important, and therefore this TensorFlow serving, PyTorch serving are a one abstraction on top of the engine that compute the actual mathematics. So one example is NVIDIA Triton is responsible for grouping multiple client requests into a batch, whereas the faster transformer receives the batch and conducts the QKV calculation. Therefore, just to give an example, if the batch size is set to 3, then the front-end inference server will pull from this queue of requests. So many users submit their requests, and the scheduler will pick 3 of them, or at most 3 of them, into one batch and dispatch it to the backend. So why do we want to batch multiple requests together? If we only have a single request, then it is a vector matrix multiplication. The vector x and the matrix wq. Then this is low GPU utilization. Whereas if we group multiple vectors of the same size together, this becomes a matrix multiplication, which the GPU, the tensor cores, like a lot, since they can use the parallel streaming multiprocessors to crunch those together. So here is a concept of throughput. What does throughput mean? It means in 1 unit of time, how many requests can you generate? Therefore, in 1 unit of time, in the first case, the throughput is 1, since we process 1 token per second. Whereas in the second case, the throughput is 4, since in 1 second, we generate 4 tokens at a time. Therefore, the bigger the batch, the higher the throughput. So now, most inference serving system uses batching, right? Because for deep learning neural networks, such as ResNet, the input is fixed, the size is fixed. You can just group them together and produce an output. In the training time, you can divide the chunk into whatever you want, so it's very efficient for batching. But what about inference, the generation phase? When the transformer model comes, we don't know how long a request will finish. Why? Even though the input size is fixed, say 3 tokens, in the first iteration we generate the 4th token, and then we feed in the 4th token into our transform model, generate the next one, and then feed it back in again. Comparing with the deep neural networks such as ResNet, which ran the model once, here in Transformer, we ran the model multiple times. And this is autoregressive generation phase. What does it do with batching? If we batch 4 requests in one group, the first request might finish in 6 seconds, whereas the second request finishes in 8 seconds. Then all of the requests in one batch needs to wait for the longest sequence to finish, and it's unpredictable how long the longest one will take. Therefore, here the white blocks are all the wasted time for the other tokens, other requests. So there are 2 problems. What are they? One is no early return. Request 1, 3, 4 have to wait for the whole batch to finish. And the second is no injection. If we have a new request, sequence 5, coming in at the time 6, we can't just inject it in since one batch needs to finish. Therefore, many customers needs to wait. Just to recap, this is called the static batching, where we take one batch, only release the batch when all the requests are finished. So this is static and rigid. For example, even if the input size is the same, we batch 2 requests, but the generation phase will be different for each. Therefore, no early return and no mid-flight injection. What is a solution? Continuous batching is proposed by the paper Orca in 2020. That was the state of the art inference. Besides Triton and the vLLM, sglang. So how does the Orca solve this problem? So instead of waiting for the whole batch to finish, why can't we, after every iteration, we check if some requests are finished early, and then we can schedule in some new batches and return the old one to the user. After iteration 1, we check if there's sequence ending. After iteration 2, we found an end of sequence token for request 2. Then here we can release x2 back to the user and then inject a new request s3, x3 here, and then ran the model again, iteration by iteration. So previously, we have to finish all the requests and then do a scheduling. But now, after every iteration, we do a scheduling. Then this is all well and good, right? And very natural. What might be some trade-off? Is this a perfect solution? So iteration, we divide this long-running sequence into 4 steps instead of 1 step. Therefore, the previous long sequence will be slower. However, the benefit is huge since we can inject mid-flight. So still, what are some other problems with this iterative scheduling? In this case, after the second iteration, we inject the new request x3. However, is it doing the same operation as x1? x1 is in its decoding phase, whereas x2 is in the prefill phase. X3 is in the prefill phase, a new request, right? And the decode and prefill are entirely different operations. Can we batch them together? No. In the third phase, the prefill and decode, their input size are different. One is 4 tokens, so the entire length of the prefill, and the second is just 1 token for decode. Therefore, but for one batch, we need them to be the same. So L and H. L is the sequence length, and H is the hidden size. So how big is 1 token? So here, the horizontal one is H, the vertical is L. How many tokens are in the sequence? So to form one batch, we need every element in this batch to be of the same L and H shape. So here L is 2, the sequence length is 2. But if we have 2 requests with different sequence lengths, 2 and 3, then if L is 2, we can't group them together since we need uniform sequence lengths. Therefore, decode and prefill definitely cannot fit together. What about all of them are prefill? If the prefill lengths are different, we can't batch them together because L is different. And second case, if both are decode but at different positions, they can't be batched together. Why? Although the input are both of length 1, right? Both of them are just 1 token. But remember, we have to fetch the KV cache. The first request already processed the 4 tokens, so the K matrix is of length 4, L equals 4. And for the second request, it's only on its second token, so only 2 tokens processed, so the K has a length of 2. Therefore, we can't group those 2 different length matrix together, and that's why when we do scheduling, if we have different inputs, different requests, we can't group them together. So when can we group them together? First is the operation is the same. So either both prefill or either both decode. And secondly, the input shape should be the same. That means the same number of tokens as input for both X and K and V. How to solve this problem? In real workloads, it's really hard to find requests of the same size, right? Many requests are different size, and some are decode, some are prefill. Therefore, it seems we can't even form a batch in real life. Then, how to solve this problem? So Orca proposes the second solution, which is selective batching. Don't worry about the name. It's like splitting the different requests in one batch to different attentions. So let's still use one batch to group different inputs. So x1 is a prefill, x1 is a decode request. In this picture, the first user is decoding on its 4th token. Second, x2 is also a decode request, is on its second index. X3 is a prefill request with 2 input tokens. X4 is a prefill with 3 input. Then what does it look like if we batch them together? X1 is 1 token, so on the left we just draw 1 token. X2 is decode, which is also 1 token. X3 is prefill with 2 tokens. X4 is prefill with 3 tokens. Therefore, this batch will consist of those 4 requests. But wait, didn't we mention we can't group them together since there are different operations, right? However, for the non-attention parts, there is linear QKV, linear projection. Remember that in transformer, we will first compute the QKV by using X multiply with WQ, WK, WV to generate those matrix. So this is a linear operation, which is called the QKV projection. So for this linear part, we don't have this attention thing. We can batch them together with this trick of flattening. That basically means we group those 4 requests and just concatenate together into a batch of 7 tokens. That's the 7H meaning. 7 is the length. And we pass this to our WQ, WK, WV, so we can do them together. But then for the attention mechanism we mentioned before, we can't do them together. So let's just split them up into different attention calculations. The first one will be a vector matrix multiplication for attention 1. The second is also attention with different Q and K size. Then there's no problem, right? And finally, we just merge those 4 streams of computation together and output this whole batch. This is all good and well, right? So no cross-attention failure. But previously, we just compute 1 attention, right? But now we compute 4 attentions, which might be very costly. So what to do? Just a recap. If we have 3 requests, the prefill will go through this QKV. Since prefill have, say, 4 tokens, it will form a attention matrix of 4x4 and output 1 token. For decode, the attention matrix will be a single line, a single row, and also form 1 token at the end. And finally, we concatenate all these tokens after the split and group them back into 1 batch. Here, since we go through attention 3 times, this is so costly. How can we reduce the number of attention? So 1 year later, in 2023, this paper called Piggyback Decoding or decode maximal batching comes in. It basically says, since although prefill and decode are different, but prefill are not that different. So we can group multiple decode into 1 and compute the attention of multiple decode with 1 attention calculation. So in 1 batch, we have 1 prefill and 10 to 100 decode usually. Instead of computing 101 attention, we can compute 1 attention for prefill and 1 attention for decode. So only 2 attentions in this case. And how is it done? How can we compute multiple decode together since their K and V can have different sizes, right? For example, the request 1 has the K tensor of shape 4 and the second has a shape 2. Well, here we can use the flash attention varlen function, and this is how this variable lens comes into play. It is designed specifically for attention with different lengths. In the above example, the sequence length is 4 and 2. The first sequence has 4, the second sequence has length 2. Then we just compute a cumulative sequence length. The CU stands for cumulative. That means from 0 to 4, it is the first sequence. And then for index 4 to 6, it is the second sequence. So those are the starting locations. And then we pass this CU sequence length into the varlen function. This flash attention will automatically compute 1 attention with those different lengths Q and K. So this, if you want to learn more, check out the flash attention video, which is one video before this, lecture 4. Very important technique. And then, problem solved, we reduced this 101 attention calculation into just 2 attention calculations. What is another benefit of hybrid batching? So batching prefill with decode. This is an interview question. So prefill and decode. For prefill, it's a compute bound operation, right? For prefill. What about decode? Decode is memory bound. Why? Because decode calculation is very simple, just one vector times a matrix, whereas prefill is a huge long matrix times a huge matrix, because the input length can be 1024, whereas here the input length is 1 for decode. Then for decode, most of the time is spent not on computation, but on loading the weights WQ, WK, WV from the global memory to the on-chip memory. So those weight matrices are pretty big, and to compute them, we need to load to the on-chip smaller memory. Since the compute is very minimal, this loading becomes proportionally large. But what if we batch prefill and decode together? Then, since prefill already loads the model weights, the decode tokens can just free ride the weights. They don't have to load them again, and this achieves super high throughput for decode. We know that decode is often latency sensitive and the throughput is very low, but now the throughput is very high. What are the results of such 2 optimizations? The red line is the baseline, the blue line is Orca. With the same latency level, the blue line is much faster than the red line. That means the blue line has much higher throughput, because remember, for Orca, we can have multiple requests coming finished at the same time iteratively, so the throughput is very high. And how does this translate to cost savings? In the baseline, if we host a GPT-3 175 billion instance for the same latency and same throughput, Orca is able to reduce the numbers by 100 or 150 times the cost saving. Because it has much higher throughput, we can early return so many requests with this iterative level scheduling, and also the hybrid batch, which improves the throughput of decode. Congratulations, you have learned the most important technique of batching, which is now using this continuous batching, which is also called in-flight batching, which is now used in vLLM, sglang, TensorRT, LLM, and all those popular frameworks. If you want to learn more about the AI engineering roadmap, check out the Substack, which has a roadmap of 5 key optimization techniques. Feel free to drop any questions. Thank you for watching.